As the 19th century came to an end, science and technology were triumphant. At the World's Fair in Paris, at the 100th anniversary of the French Revolution in 1889, there was a fantastic display of new technology, especially the world's tallest artificial structure, by far, the Eiffel Tower and its elevators. Fantastic new thing, unlike anything that man had ever been built before. To rival that, at the 400th anniversary of the discovery of America by Columbus, the Americans in Chicago had the Great Columbian Exhibition, where an enormous area was lit by artificial light. People danced throughout the night in this illuminated area. Many other technological devices, I believe the primitive version of the phonograph and the telephone were displayed. Technology was triumphant, not only elevators and air conditioners, but automobiles. It was clear that science had done a good job. And many people thought that indeed science had come to an end. It had done everything it could possibly have done. Artificial dyes in chemistry, electrical devices of all sorts, Maxwell's theory, Newton's theory, what more had to be done? But in the waning years of the century, a number of striking discoveries took place. I'll mention just three of them. The discovery, completely unanticipated, of X-rays, of a new method of finding broken bones and finding cavities in your teeth, and of fitting your shoes, because in the old days, X-rays were used in shoe stores to make sure your shoes fit. A wonderful new technology of X-rays. Then, to everybody's surprise, the discovery of radioactivity, a apparently infinite new source of energy involving processes that could not be explained by anything, any physics that existed at the time. And then, climaxing it, the discovery of the electron, of the first elementary particle, the particle that gives rise, is the basis to all electrical phenomena. We call it electronics, we call it electricity. It all depends on the motion of electrons. Something was about to happen. Two great revolutions were about to take place as soon as the 20th century began. One was the development of quantum mechanics, the realization that Newton's mechanics fails for things that are too small, things like atoms. And secondly, the Einstein's special theory of relativity, which also said that Newton's theory fails whenever things move too quickly. For things too fast or things too small, we needed new theories. One of the problems that arose that was not yet solved had to do with thermal energy, sometimes called black body radiation. The radiation produced by a hot oven, by heating things up in a fire. Now, if you have an iron and you hold it up to your face, the iron temperature of the iron is maybe 150 degrees centigrade or so, a little bit above the boiling point of water. If you bring it near your face, you can feel that it's radiating heat. It's radiating infrared radiation. If you take a piece of iron and heat it up even more, it will emit a lot more heat and it will turn a dull red. Let's continue to heat up this piece of metal. If you heat it more, it turns a different color. It turns orange, and then yellow, and then white, and then blue-white, as it gets brighter and brighter and brighter. This is the phenomenon of thermal radiation, and the scientists at the time could not understand this phenomenon. They could not find a formula that explained how the color would change as you heat something up and how the amount of energy radiated, produced by a hot object, increases as it gets hotter and hotter. There were some detailed empirical laws describing what's going on, but there was no one formula that could be derived that could explain thermal radiation. There was no formula until the year 1900, when such a formula was invented by a German physicist named Max Planck.
Max Planck nasce a Kiel, in Germania, nel 1858. Quando è ancora un bambino, si trasferisce con la famiglia a Monaco, dove frequenta l'università, dedicandosi appassionatamente allo studio della matematica e della fisica. Grazie alle sue brillanti doti, a soli 28 anni, nel 1885, Planck ottiene la cattedra di fisica all'Università di Kiel. Pochi anni dopo viene chiamato a succedere al fisico e matematico Gustav Robert Kirchhoff all'Università di Berlino, dove fino al 1926 dirigerà l'Istituto di Fisica Teorica. È qui che vede la luce la teoria dei quanti. Con le sue ricerche Planck diventa in pochi anni uno dei fisici tedeschi più autorevoli del tempo e nel 1918 riceve il prestigioso Premio Nobel per la fisica. A Berlino viene nominato segretario dell'Accademia delle Scienze e nel 1930 eletto presidente della Società Kaiser Wilhelm per lo sviluppo della scienza, la principale associazione degli scienziati tedeschi. Per la sua contrarietà al regime nazista, lo scienziato sarà allontanato dall'incarico nel 1937. Ma dopo la fine della guerra, nel 1948, la celebre istituzione gli renderà onore cambiando il nome in Società Max Planck. Gli anni delle due guerre mondiali e del nazismo sono segnati per Planck da grandi tragedie personali. Le morti dei suoi figli si succedono drammaticamente, ma negli ultimi anni della sua vita, lo scienziato ormai anziano potrà ancora vedere la caduta di Hitler e la fine della guerra. Morirà a Göttingen nel 1947.
Planck struggled, and on the basis of existing theory, he could not make such a formula. He had to cheat. He had to cheat by saying that, well, he was thinking about a hot surface, and a hot surface is emitting light. And what he had to assume is that the light is emitted in little bundles, which he called quanta, the origin of the word quantum mechanics. It's like when you go to the grocery store, you can't buy 3 ounces of milk or 2.6 ounces of milk or 1 1/4 quarts of milk. You buy either a pint or a quart, but it comes in discrete bundles. It doesn't come continuously. And so Planck had to make this crazy assumption that light is emitted in bundles and that the size of a bundle varies with the frequency of the light. So a bundle of red light carries less energy than a bundle of violet light. With that completely crazy hypothesis, he made a formula, and that formula worked perfectly. Wonderful new formula, except he had to go outside of the realm of classical physics. He had to introduce a new physical constant, which nobody had ever heard of before. It became known as Planck's constant, and only using this crazy constant could he derive this strange formula. Now, that would remain a mystery for 20 years or so, 25 years. It began to be understood a little bit better when Einstein came into the picture in 1905. Now, 1905 is a magical, miracle year for Einstein. He did many, many things in that year. One of the things he did had to do with what Planck had done.
A partire dalla prima metà del XX secolo inizia lo sviluppo della meccanica quantistica, un complesso di teorie fisiche capaci di descrivere la realtà del mondo degli atomi e delle particelle elementari. La meccanica quantistica permette di interpretare i fenomeni che si verificano a livello atomico, che non potrebbero trovare spiegazioni esaurienti nella meccanica classica. Quando Maxwell, Boltzmann e altri fisici iniziarono a studiare le proprietà atomiche e molecolari nella seconda metà del XIX secolo, immaginarono che le leggi di Newton costituissero ancora una buona descrizione per questo tipo di fenomeni. Per esempio, gli elettroni erano concepiti come corpuscoli molto piccoli di cui si poteva determinare la posizione e la velocità ad ogni istante in modo analogo ai pianeti del Sistema Solare. Ma ciò che è completamente definibile nel mondo della fisica classica non lo è più nel mondo degli atomi. Infatti, come poi dimostrò il principio di indeterminazione di Heisenberg, uno dei pilastri fondamentali su cui si basa la meccanica quantistica, la posizione e la velocità di una particella non possono essere determinate contemporaneamente. Tuttavia, la fisica classica continua a fornire buone approssimazioni a livello macroscopico, descrivendo la velocità e le distanze che entrano in gioco nella nostra vita quotidiana.
Einstein, fascinated by what Planck had done, tried to understand it in more detail. And he found that, first of all, Planck's derivation of his formula was incomplete. There was a step missing. And that step required that light not only is emitted in bundles and absorbed in bundles, but it travels in bundles. So light consists of bundles of energy. Light consists of corpuscles or particles. So he had made a full circle. Remember, Newton said light is particles. Maxwell said light is waves. And now we have Einstein saying, well, it's not that simple. Sometimes light behaves like waves, but sometimes it behaves as if it were particles. And this is a completely crazy statement. It's hard to see how this can possibly be understood in terms of any classical thought. Indeed, it can't. The whole idea of arguing whether light is particles or waves makes no sense, because the word particle and the word wave are things that we have learnt as human beings with human experiences. But in the micro world, the words that we have don't have any applicability. Light, it turns out, is not a particle. Light is not made of waves. Light is light. Sometimes it shows itself as a wave, sometimes as a particle. It's like an Indian god which can take many different avatars. Einstein argued that light can behave as a particle and can behave as a wave, and he showed how the particle-like behavior could manifest itself. It was known that when light, in particular ultraviolet light, impinged upon a metal, it would drive off electrons. And Einstein argued in the following way. He said, what's going on is that a particle of light, which came to be known later as a photon, when a photon enters a metal, it can give its energy to an electron. And that electron will come out with all of the energy of the photon, less the cost of extracting the electron from the metal. It takes a little bit of energy to get the electron out of the metal. So therefore, Einstein said, when you increase the frequency of light, when you go from one frequency to a higher frequency, proportionately the energy of the electron coming off should increase. If the frequency were less than the cost of removing the electron, the light should not produce electrons. Visible light hitting a piece of iron or tin does not produce electrons. Ultraviolet light, higher frequency, does produce electrons. And the electrons have more energy if the light is a higher frequency. Now, the wave theory of light says something completely different. According to the wave theory, light of any frequency ought to produce electrons. Even red light should produce electrons if it were sufficiently bright. So turn up the intensity, an electron should come out. But it was known that this didn't happen. You had to increase the frequency. This effect is called the photoelectric effect.
Nel 1905 Einstein, prendendo spunto dalla teoria dei quanti di Planck, ipotizzò che anche la luce esistesse sotto forma di pacchetti di energia che in seguito presero il nome di fotoni. L'energia di un fotone è proporzionale alla sua frequenza. Quindi maggiore è la frequenza, più elevata è l'energia. I fotoni di luce con frequenza elevata riescono, quando colpiscono un metallo, a liberare gli elettroni e a generare corrente elettrica. Questo fenomeno è conosciuto come effetto fotoelettrico. L'effetto fotoelettrico trova ampia applicazione nella tecnologia d'uso quotidiano. Per esempio, è alla base del meccanismo che regola l'apertura e la chiusura automatica delle porte degli ascensori. Quando tra le porte non ci sono ostacoli, il raggio luminoso che le attraversa colpisce una cellula fotoelettrica. Gli elettroni prodotti dall'effetto fotoelettrico attivano un circuito che causa la chiusura della porta. Nel momento in cui si entra nell'ascensore, l'interruzione del raggio luminoso impedisce l'attivazione della chiusura delle porte, evitandoci di finire schiacciati. L'effetto fotoelettrico è anche sfruttato nei pannelli solari fotovoltaici, che trasformano la luce del sole direttamente in energia elettrica. Nel 1969 i fisici Willard Boyle e George Smith, basandosi su questa teoria, svilupparono il primo sensore di immagine digitale CCD, dall'inglese Charge Coupled Device, ovvero dispositivo ad accoppiamento di carica. I sensori CCD catturano i segnali degli elettroni e li trasformano in pixel, i punti di una immagine digitale. I CCD sono il cuore di macchine fotografiche digitali, videocamere, scanner e di ogni dispositivo dotato di un occhio elettronico. Per la loro straordinaria invenzione, Boyle e Smith nel 2009 furono insigniti del premio Nobel per la fisica.
Ernest Rutherford is one of the greatest physicists of the early 20th century, and the only one I can think of who was born in New Zealand, educated in New Zealand. On or around 1911 or 1912, he was working in England, and he was working with radioactive particles, with alpha particles, particles produced by radioactive substances. He got his alpha particles from polonium, which is an element that had been discovered just a few years before by Madame Curie. But he used these particles, these alpha particles, to do many interesting things. And the most interesting was to discover the atomic nucleus. What was the atom? Around the time of Rutherford, what did people believe an atom to be? An atom had a certain size, about 10 to the minus 10th, that's to say a 10,000th of a millionth of a meter, 10 to the minus 10th meters, tiny, tiny thing. It was supposed to be a uniform glob with electrons in it, like raisins in a pudding. It was called the plum pudding model of the atom. Everyone believed atoms to be these things which had the size of the atom. But it wasn't like that at all. What Rutherford discovered, we all know today, we learn in grammar school, that most of the mass of the atom lies in its tiny nucleus, and most of it is empty space. Empty space in which there are these electrons moving around quantum mechanically. In fact, if you made the atom as big as a football field, the nucleus, in which 99.9% of the mass of the atom is, would be the size of an olive in a football field. The nucleus is very tiny, and most of the mass of the atom is in its tiny nucleus. So this was a new and revolutionary picture. The atom consisted of a tiny nucleus with electrons moving around outside of it. The planetary model, a little bit like the solar system. The solar system has the sun in the middle and the planets going around it, held together by the gravitational force. In a similar way, an atom consists of a nucleus with a number of electrons, depending upon where that atom is in the periodic table, a lot of electrons going around the nucleus as a result of the electric force, the attractive electric force between the positively charged nucleus and the negatively charged electrons. And we all learned in school the new realization of the structure of the atom. But there were problems lurking with this explanation. Let's consider the simplest atom. The simplest atom is the hydrogen atom. The hydrogen atom consists of a very simple nucleus, consisting of a particle called the proton, surrounded by one electron. So it's a simple nucleus with positive charge, 1 unit of positive charge, and the neutral atom has a nucleus and 1 electron going around it. What could be simpler? Now, trouble is that what tells you how big the atom should be? Because if you imagine a star with 1 planet, that planet could have an orbit like Mercury's orbit, could be very close to the sun, or it could have an orbit like Neptune's orbit or Uranus' orbit and be very far from the sun. It could have any orbit whatever. But it was an empirical fact that all hydrogen atoms have the same size. What law of physics was it that told you that you couldn't have just any orbit of the electron going around the proton. It always was in the same orbit when the hydrogen atom was just sitting there at rest. What was going on? It was worse than this, because if you imagine a hydrogen atom with an electron, the electron is going around in a circular orbit. But we learned, Maxwell taught us, that if an electron, if a charged particle is moving in a circle, it radiates light. And so this electron would radiate light, and it would fall into the nucleus, and the atom would collapse. It would collapse in a tiny fraction of a second. So this was another serious problem with the planetary model. It just didn't make any sense. The atom should be unstable, and there is no reason for all hydrogen atoms to behave the same way. Different hydrogen atoms should behave differently. Enter a young Danish physicist who was, in fact, visiting Rutherford when Rutherford made his great discovery. Niels Bohr went back to Denmark and began the invention of quantum mechanics. He set about trying to resolve these two problems: why the hydrogen atom is stable, and why all hydrogen atoms are the same size. And he realized that classical physics could not solve this problem. He needed to invoke Einstein's particle interpretation of light, and he needed to make some special kind of rule to understand which orbits were okay and which orbits were not. He introduced his own ad hoc rules. He speculated that, well, technically what he said is the angular momentum of the electron, that's how much it's turning around the proton, had to be equal to a certain, an integer multiple of Planck's constant. And so, with this crazy rule, he explained why all hydrogen atoms are the same size. He explained why the hydrogen atom is stable, why the electron doesn't fall into the proton. And moreover, he explained the spectrum, the visual spectrum of hydrogen. It had been known for many, many years that each chemical element can vibrate in a certain discrete number of ways. It can produce light of certain frequencies and no other frequencies. It has a characteristic spectrum. When you put some sodium in a flame, such as when the pot boils over, you're cooking soup and you boil it too much and a little bit of it goes into the fire turns yellow. It turns yellow because sodium has some characteristic yellow spectral lines. Hydrogen was known to have 5 visible spectral lines, and they satisfied a rather simple formula that no one understood. Bohr derived that formula. He explained all of the properties of hydrogen on the basis of some crazy rules that had no justification except that they worked. It was a trick. It explained a lot. But what did it all mean? How could we explain the success of Bohr's crazy rules? It would take another 13 years before the solution would emerge. There was a time when Einstein was completely enamored of this new quantum theory of Bohr. He loved it because Bohr not only explained the spectrum of the hydrogen atom, but he also explained the spectrum of the ionized helium atom, which produced some crazy spectral lines that in a distant star that no one could understand. Meanwhile, soon after Bohr did his epical work in 1913, a young Frenchman was studying these ideas. The Frenchman was a very royal Frenchman. He was a prince, Prince Louis de Broglie. And in his thesis, he made a fascinating speculation. He said, Einstein has argued and proven to the world that light, which most people think of as a wave, can behave as a particle. Wouldn't it be necessarily true then that particles, say electrons, which everybody believes are particles, shouldn't they sometimes behave like waves? Shouldn't it be true that light is both a particle and a wave, and electrons are both particles and waves? And he argued that if this crazy idea were true, it ought to be possible to test it by looking for interference patterns. When a beam of electrons would hit a crystal, they should reflect back. Sometimes the waves should agree with one another, and sometimes they should cancel, and you should see a pattern of interference, just as you did with light. And indeed, when the experiments were done, such interference patterns were seen, and de Broglie's waves, which were called then de Broglie waves or matter waves, were certain to exist. There were these wave properties associated with matter. What could it all mean? Well, we come now to the development of quantum mechanics, something which took place in the heads of two independent geniuses in the year 1926.
Dopo Planck, la meccanica quantistica viene portata a piena maturità da altri grandi fisici del Novecento, tra cui un posto di rilievo spetta a Werner Heisenberg. Nato a Würzburg nel 1901, Heisenberg studia fisica a Monaco e Göttingen, accanto ai maggiori scienziati tedeschi del tempo. Nel 1924, grazie a una borsa di studio dalla Rockefeller Foundation, si reca a Copenaghen per lavorare con Niels Bohr, altro grande padre della nuova fisica. In collaborazione con Bohr, nel 1925, elabora una formulazione della meccanica quantistica denominata meccanica delle matrici. Risale al 1927 il famoso principio di indeterminazione, che contiene uno degli effetti più noti del carattere probabilistico della teoria dei quanti. Il principio afferma che non è possibile conoscere simultaneamente la velocità e la posizione di una particella con certezza, perché la misura della posizione, quindi l'intervento dell'osservatore, disturba necessariamente la sua velocità. Nel 1932 Heisenberg è insignito del premio Nobel per la fisica. Durante la Seconda Guerra Mondiale va a dirigere il programma nucleare tedesco, determinando una brusca rottura dei rapporti con l'amico Bohr, che fugge invece dalla Danimarca dopo l'occupazione nazista e negli Stati Uniti va a collaborare alla costruzione delle armi atomiche statunitensi. Dopo la guerra prosegue il suo lavoro di fisico in Germania, dedicandosi alla fisica del plasma, ai processi termonucleari e alla teoria di campo unificata delle particelle elementari, mentre si moltiplicano i riconoscimenti e i premi. Muore a Monaco nel 1976.
Well, the quantum ideas were so radical that they attracted the youngest and most ambitious scientists. The older scientists could not accept these crazy new ideas. One of the young Turks, a German in fact, was Werner Heisenberg. And Heisenberg thought about the ideas of Bohr. He realized that they must in some way be correct, and he tried to fashion a theory. He first realized that one of the consequences of Bohr's work and the work of de Broglie was the uncertainty principle, was the fact that an experiment, no matter how precise, could not measure both the position and the momentum of a particle, let's say the position and the velocity of a particle, at the same time. And he had a wonderful explanation for why you couldn't do this. He said, well, let's suppose we're using a microscope to look at some real tiny little thing. Well, a microscope uses light, and light has a certain wavelength. So you can't see anything much smaller than the wavelength of the light. The size of your probe is the smallest object you can see with a given probe. And because light has a certain wavelength, you can't measure things smaller than that wavelength. But no problem, just use ultraviolet light, which has a shorter wavelength. Or if that's not enough, use X-rays, which have an even shorter wavelength. So you can, by using shorter and shorter wavelengths of light, measure the position of an object with any degree of accuracy you want. But what about measuring the speed of the object? To measure the speed of the object, you have to remember, when using light, you have to hit it with at least one particle of light. And if you hit it with one particle of light, you're changing its speed. But you say, no problem, because I can hit it more and more gently. I can hit it with a lower and lower frequency. So with a low frequency light, you can measure the speed, and with high frequency light, you can measure the position. But the better you measure the position, the more you screw up the speed, and the better you measure the speed, the more you screw up the position. You can't measure them both. And this was a fundamental consequence of the theory that he was about to invent. And he, Heisenberg, and Bohr, and Einstein had many arguments about whether this was really true, whether it was true that there was a fundamental limit to how well you could measure things. This changes the rules completely of classical mechanics, because in classical mechanics, according to the mechanics of Newton, if you measure the position and the velocity of something, you will know what it will do forevermore. And now we were learning that you can't measure the position and the velocity. So you can't know what it will do forevermore. Heisenberg invented a new scheme, which he called matrix mechanics, which gave a logical foundation to Bohr's rules. He invented a theory. Matrix mechanics was a formulation of quantum mechanics, which included Bohr's arbitrary rules, but which was much more precise and much more specific, and was mathematically self-consistent. It was indeed a theory of quantum mechanics. He discovered this theory in 1926. Quantum mechanics actually had two fathers. We've spoke about one of them, Werner Heisenberg. This fellow here, and he developed quantum mechanics in the form of matrix mechanics. A very young man who became a very important physicist in Germany, very highly regarded. At the same time that Heisenberg invented matrix mechanics, an Austrian physicist, not quite so young, while he was on vacation with his mistress in a ski resort in Austria, during that week of pleasure, created wave mechanics, another form of quantum mechanics, another theory, which also embodied all of the rules of Niels Bohr. So there were two quantum mechanics that existed. Matrix mechanics, which involved a certain kind of algebra, algebraic manipulations, and Schrödinger, which involved a wave equation, rather like the equation that describes heat or electrical fields, a differential equation, a different, completely different kind of mathematics. And according to Schrödinger, there was an equation, which we call Schrödinger's equation, which describes the matter waves, the de Broglie waves of the electron in a hydrogen atom. It's a wave equation describing the wave function of the electron. Heisenberg didn't have any wave function. He had these algebraic structures called matrices. A very different point of view, both of which made the same predictions. How could this be? Enter a third father. There was a sort of a mediator between Schrödinger and Heisenberg. His name was Max Born. He was a German Jew. He had to leave Germany during the Second World War. Max Born looked at what Schrödinger had done and found that it was completely consistent and good. And he looked at what Heisenberg had done and found that it was completely consistent and good. But he realized that the two theories are equivalent to one another, that what Schrödinger had done in his language of calculus was exactly the same as what Heisenberg had done in his language of algebra, with just a different mathematical realization of precisely the same theory. And furthermore, Max Born realized what these matter waves were, these waves that Schrödinger was describing. They weren't really waves of matter. They had to do with probability. Where the wave function is big, the particle is likely to be. Where the wave function is small, the particle is not very likely to be. And this is the probabilistic interpretation of quantum mechanics, which is what we all believe today. The two theories are one. All three of these participants in this exciting adventure would receive the Nobel Prize for their contributions to human learning. But there were a number of things missing from the theory.
Il fisico austriaco Erwin Schrödinger, noto per il suo apporto alla meccanica quantistica, fu il primo ad ipotizzare, nel 1926, la possibilità teorica di un fenomeno dai risvolti fantascientifici, definito da Einstein inquietante azione a distanza. Si tratta del entanglement quantistico, che prevede che due o più particelle, dopo un certo periodo di interazione reciproca, una volta separate, continuino comunque a mantenere una correlazione tra loro. Queste particelle rimangono cioè in qualche modo legate indissolubilmente e ciò che accade a una di esse si ripercuote immediatamente sull'altra, anche se sono separate da una distanza di milioni di miliardi di chilometri. L'ipotesi che una particella potesse influenzarne un'altra istantaneamente era inaccettabile per Einstein, in quanto violava uno dei postulati della teoria della relatività, secondo la quale nulla può viaggiare a velocità superluminale, ovvero superiore a quella della luce. Eppure, per quanto apparentemente bizzarro, l'entanglement quantistico sta avendo ricadute concrete in campo scientifico e tecnologico. La possibilità di trasmettere qubit, ovvero unità di informazione quantistica a velocità superluminali, permetterà di sviluppare computer quantistici. Questi computer, usando atomi e molecole come processori, saranno in grado di raggiungere potenze di calcolo esponenzialmente più elevate rispetto ai nostri attuali PC. Di fatto si tratta di un vero e proprio teletrasporto di dati. Il primo esperimento di teletrasporto realizzato con successo fu condotto nel 1997 da Anton Zeilinger, fisico austriaco e professore all'Università di Vienna. Insieme alla sua equipe riuscì a teletrasportare con successo fotoni, cioè particelle di luce, da una riva all'altra del Danubio. Tuttavia siamo ancora ben lontani dal teletrasporto dell'immaginario fantascientifico, come quello utilizzato per esempio dai protagonisti di serie televisive come Star Trek.
One of the great challenges for quantum mechanics was to try to explain the periodic table of the elements. Mendeleev's great accomplishment of the 19th century to display the different chemical elements in the form of a table which indicated their periodic properties. Could this be explained? Could quantum mechanics do this? Could quantum mechanics get beyond just explaining the structure of the hydrogen atom? And this posed a number of difficulties. It was not clear how to do this. There was something missing. And the concept that was missing is called electron spin. Yeah, the electron has a very strange and essentially quantum mechanical property called spin. That is to say, it's turning around its own axis in a sense. It can be spinning this way, or it can be spinning that way. Two ways the spin can point, or if you don't like that, up and down, but only two different directions of spin. You can choose them as you will. Then a couple of Dutch physicists in the 1920s, Goudsmit and Uhlenbeck, showed experimentally, they sent a beam of electrons through a magnetic field, and indeed, the beam split into two, corresponding to the two spin states of the electron. And once the concept of spin was revealed, we could understand why it is that the helium atom has no chemical properties. It's a stable atom which doesn't react or combine with other atoms. And then you build up bigger and bigger atoms until you come to neon, which is another inert gas. And we have this so-called shell structure, periodic structure, the periodic table. Once spin was discovered, physicists realized that they understood the basic rules of chemistry. Chemical force was no longer mysterious. It was a consequence of quantum mechanics. The behavior of the different chemical elements as exhibited in the periodic table could be deduced a priori with no further hypotheses and no further experiments. It was a remarkable realization, the basic understanding of chemistry, which of course is not to say that chemists had become obsolete. There were still lots of things for chemists to do, as there are today for chemists to do. Knowing the rules of chess does not make you a grandmaster. Just because we understand the basic rules of chemistry doesn't mean that we are chemists and that we can do whatever we want chemically. Another young scientist played a key role in the development of quantum mechanics and in the explanation of the chemical properties of chemistry, and that was Wolfgang Pauli. Wolfgang Pauli introduced what has become known as the Pauli principle. In its original form, it was the statement that not more than two electrons can do the same thing at the same time. a crazy-sounding principle. When spin was discovered, when it was realized that the electron had two different spin states, Pauli's principle became a little bit simpler. It became not more than one electron can do the same thing at the same time, because one electron could spin up and one electron can spin down. And now, with Pauli's principle and the notion of spin, we immediately could understand why hydrogen is a very chemically active material, hydrogen, which has only one electron, but helium, which has two electrons in the same state, one spinning up and one spinning down, is a very happy chemical element. It has filled up its quantum states. There's nothing for it to do. It can't steal someone else's electron. It can't give an electron to anyone else. It's happy unto itself. It's an inert gas. So that the existence of these funny chemical elements, helium, neon, argon, xenon, and krypton, which have no chemical properties, was explained by Pauli's principle. Now we have a small problem. We have Schrödinger's equation, which is the basis to quantum mechanics, but Schrödinger's equation does not include a description of spin, and Schrödinger's equation is not consistent with Einstein's theory of relativity. No spin, no relativity. Heisenberg and Schrödinger both knew that the theory they were developing was not consistent with Einstein's theory of relativity, but they couldn't do any better. Pauli, struggling to improve Schrödinger's theory, invented an equation called the Pauli equation, which incorporates spin. It is a Schrödinger equation with spin, but it doesn't deal with relativity. Some other guys invented an equation which is relativistically invariant, which is consistent with Einstein's theory, but did not involve spin. To describe the electron, we have to have a theory which A is compatible with Einstein, B includes spin, because electrons have spin. There was no such theory until 1929. And that brings us to yet another, the youngest of them perhaps, young physicist, Paul Adrien Maurice Dirac. Dirac invented the Dirac equation, as it is known. It's a very simple equation. Looks simple, but there's a lot that goes into it. It is a relativistic equation. It's consistent with the Einstein's theory, and it includes a description of spin, and it works. It describes the electron. The behavior of an electron in an electromagnetic field is explained completely by this wonderful equation. But as Dirac said to me, my equation, he said, was smarter than I was, because this equation that he wrote down, which worked so well, had two kinds of solutions. It had solutions with positive energy, and that described electrons, but it had some unphysical solutions with negative energy, which makes no sense. So the question was, what do you do with these other solutions? Well, at first, Dirac thought that maybe his equation described two kinds of particles. There were only two kinds of particles known: electrons and protons. Negatively charged electrons, positively charged protons. But that didn't work, because the equation said that the other kinds of particles, besides electrons, had to have the same mass as electrons, but opposite energy or opposite charge. And what Dirac finally realized, his equation was telling him that in addition to electrons, which are negatively charged particles, there had to be positively charged particles with the same mass, particles which would become known as positrons. But there was no evidence for positrons. Nobody had ever seen a positron until an American physicist, Carl Anderson, discovered them by accident in cosmic rays. He wasn't looking for them. He didn't even know about Dirac's prediction of the existence of positrons, but he found them. He found antiparticles, the first known form of antiparticles, which, by the way, are rather useful today. When you go to the doctor's office, he may prescribe for you a PET scan, and what that is a way of studying the interior of the human body, making use of antimatter, making use of positrons. So it was, oddly enough, antimatter, a very practical discovery, 1932. And we had a relativistic theory that described electrons with spin and their antiparticles, also with spin. And we had developed the beginning of what is called relativistic quantum mechanics, a new form of quantum mechanics that was consistent with relativity. And just like Maxwell's theory of electromagnetism, which gave something new, it explained light, the theory of relativistic quantum mechanics explains something very, very new as well.
La formulazione generale della meccanica quantistica si deve, alla fine degli anni '20, al fisico inglese Paul Dirac, nato a Bristol nel 1902. Dirac studia a Bristol e si specializza in fisica e matematica a Cambridge, dove a 30 anni diventa professore. La sua figura è rimasta relativamente sconosciuta al grande pubblico, a differenza di altri fisici geniali suoi contemporanei, come Einstein, Bohr, Heisenberg e Fermi. Era d'altronde un uomo riservato e di poche parole, timido e problematico, di cui si narrano molti aneddoti curiosi, come l'abitudine di camminare sempre attaccato ai muri e l'uso di rispondere solo a monosillabi. Eppure questo strano personaggio in pochi anni ha consegnato alla fisica moderna alcuni contributi fondamentali che gli sono valsi nel 1933 l'assegnazione del premio Nobel insieme a un altro grande fisico, Erwin Schrödinger. Dirac resterà il più giovane premio Nobel nella storia della fisica teorica. Alla fine degli anni '20, non ancora trentenne, Dirac va in cerca di una nuova teoria capace di descrivere il comportamento delle particelle subatomiche anche ad alte energie, comportamento che non era possibile spiegare con la teoria quantistica di Schrödinger. Questa ricerca lo porta a formulare la meccanica quantistica relativistica, che attualmente descrive con successo il comportamento di tutte le particelle note. L'aspetto più affascinante della sua teoria è che prevede per ogni particella dotata di carica l'esistenza di un'altra particella dotata di massa identica e di carica opposta, quella che oggi chiamiamo antiparticella. Nel 1930 Dirac può così ipotizzare l'esistenza del positrone, con la stessa massa e carica dell'elettrone, ma di segno opposto, aprendo tutta una serie di ricerche sull'antimateria, che negli anni successivi porteranno, grazie al lavoro di altri brillanti scienziati, le prime conferme sperimentali.
We're in the 1930s now, and people are trying to understand one of the basic steps of the Bohr model. According to Bohr, if an atom is in an excited state, it falls to a lower state and emits a photon, produces a photon. How are particles produced and destroyed? Particles can be produced, particles can be destroyed. A photon can be converted into an electron and positron. An electron can annihilate a positron, producing photons. Photons can be produced, photons can be absorbed. How do these processes take place? What is the mechanism for the production and annihilation of particles? And the answer to that question was a question that really was not even asked until the 20th century. It's a question we did not dare ask until we had a relativistic quantum mechanics, because it turns out that relativistic quantum mechanics, also known as quantum field theory, is a theory of the creation and destruction of particles. It explains how this takes place. But it took a while for the theory to emerge. It took a while because simple attempts to make a consistent theory of interacting electrons and photons ran into big problems because the mathematics produced absurd results. You would calculate something and it would come out to be infinite. That doesn't make any sense. And this simply could not be understood until, inspired by an astonishing experimental discovery, in 1948, physicists began finally to attempt the creation of a theory that could describe particle creation and particle destruction. And 3 people would win the Nobel Prize for the invention of the theory of quantum electrodynamics. This is the quantum field theory that describes electrons, positrons, and photons, light, electrons, and positrons. And the theory was developed by Julian Schwinger, by Richard Feynman, who was a professor at Cornell while I was an undergraduate at Cornell, but he then went to California Institute of Technology. He and Schwinger, and independently, but people didn't know it at the time, Tominaga, Shinichiro Tominaga, had developed this theory of the creation and destruction of particles, quantum electrodynamics. And that was a landmark development. We finally understood light and electrons and the behavior of atoms completely, including the jumps that Bohr spoke of, the emissions of photons as a particle moves from one state to another. We had a mechanism for describing such creations and destructions. It was a wonderful theory. It was a prototype for the other interactions of physics. It was a prototype for understanding the nuclear forces, the weak nuclear force and the strong nuclear force. It was clearly going to be even more important than it seemed to be at first sight. Jump now to 1957. Schwinger had not yet got his Nobel Prize for his contribution to the development of quantum electrodynamics. He would very soon get it. I was his graduate student. He told me that surely there must be a way of extending the theory of quantum electrodynamics, of allowing it to explain the so-called weak force. He said to me, go make a theory, a unified theory of weak and electromagnetic forces. I was just a young graduate student. I didn't know what he was talking about. I tried. I tried, and I tried, and I failed. And finally, since I made a good effort, I graduated. But eventually, with the help of my friends, we created just such a theory as Julian Schwinger had imagined, an extension of quantum electrodynamics, an extension of Maxwell's theory of electricity and magnetism, but one that could also explain how protons turn into neutrons, how neutrons turn into protons, how nuclear weapons work, how the sun burns. All those things could now be explained in terms of a single consistent theory, the electroweak theory.
Ogni fenomeno che accade nell'universo è frutto dell'azione di 4 forze fondamentali. La forza gravitazionale, che agisce su tutti i corpi che abbiano massa e energia. È la forza più debole tra le 4, ma è in grado di agire a lunghe distanze. La forza elettromagnetica, che sta alla base non solo dei fenomeni elettrici o magnetici, ma anche dei processi chimici o biologici. La forza nucleare forte, che è l'interazione più forte, ma dal raggio d'azione molto breve. Agisce all'interno dei nuclei atomici, tenendo insieme protoni e neutroni. La forza nucleare debole, che si manifesta nel decadimento radioattivo, cioè nella disintegrazione di atomi radioattivi, in cui un neutrone si trasforma in un protone. I fisici teorici sono impegnati nella progressiva unificazione di queste 4 forze in un solo modello, dimostrando in tal modo che ognuna è un aspetto di un'unica forza. Ad esempio, prima che Maxwell dimostrasse che elettricità e magnetismo erano l'una l'aspetto inevitabile dell'altro, la forza elettrica e quella magnetica erano considerati 2 fenomeni separati. Nel 1968, 3 fisici, Glashow, Salam e Weinberg, crearono una teoria che unificava la forza debole e quella elettromagnetica. Dimostrarono che a temperature o a energie sufficientemente elevate, come ad esempio la temperatura raggiunta dall'universo poco dopo il Big Bang, le due sono un'unica forza a tutti gli effetti. Questa teoria fu chiamata interazione elettrodebole e i 3 fisici ricevettero nel 1979 il premio Nobel per la loro scoperta.
Quantum mechanics, it must be admitted, is not just an abstract discipline. It's like some exotic branch of mathematics. It's rather practical. And the devices that we all have in our pockets today are very, very quantum mechanical devices. Your cell phone is a quantum mechanical device. It makes use of the photoelectric principle to take pictures. It makes use of transistors, which are intrinsically quantum mechanical devices. When I was a lad, when I was a young boy, a radio consisted inside of about a dozen tubes, vacuum tubes. And I remember when the radio would break, you would take all the tubes in a paper bag and go to a radio store and push the tubes into a testing machine until you found out which tube was broken, and then you would buy a 6H6 tube, and that would fix the radio. Well, that was a very primitive and not very quantum mechanical device. The vacuum tube is a very classical device. The transistor, which appeared in the 1950s and revolutionized radios and all electronics, is an essentially quantum mechanical device. The laser and your CD player or iPod depend crucially on the behavior of lasers. Your computer makes use of a laser to read the information present on the disk. Is, again, a thoroughly quantum mechanical device. So that we are more and more, not just quantum mechanical, but quantum field theoretic device. Let us change the subject a little bit and mention Einstein's general theory of relativity, his theory of gravity. That theory is at the heart of how a GPS system works. If we didn't understand Einstein's general theory of relativity, we could not have developed the global positioning system. We could not have these little maps in our cars that keep us from getting lost, because physics, no matter how obscure and seemingly irrelevant it is, sooner or later will affect your life or the lives of your children.